Linear programming, LP, is a mathematical way to choose the best possible outcome when you have limited resources. Think of an MBA student as a manager who must decide how much of each product to produce, how many employees to schedule, or how much money to invest, while staying within budget, labor, or material limits. Decision modeling is the broader process of turning a real-world business problem into a set of numbers, variables, and equations that a computer can solve. In MBA exams, you are expected to 1. Identify the decision variables, 2. Write an objective that reflects profit, cost, or utility, 3. List the constraints that represent scarce resources, and 4. Solve or interpret the model. LP is powerful because it gives a clear, optimal answer and also tells you how sensitive that answer is to changes in the data, which is exactly what managers need for strategic planning. Decision variables: what you control. Example, let X equal number of standard chairs produced, Y equal number of deluxe chairs produced. Objective function: what you want to maximize or minimize. If profit per standard chair is $30 and per deluxe chair is $50, the profit function is maximize Z equals 30X plus 50Y. Constraints: the limits on resources. Suppose you have at most 200 labor hours, each standard chair needs 2 hours, deluxe needs 3, and 150 units of wood. Standard uses 1 unit, deluxe uses 2. The constraints become 2x plus 3y less than or equal to 200. X plus 2y less than or equal to 150. X greater than or equal to 0, Y greater than or equal to 0. You cannot produce a negative number. The complete LP model is therefore maximize Z equals 30x plus 50y. Subject to 2x plus 3y less than or equal to 200. X plus 2y less than or equal to 150. X, Y greater than or equal to 0. This formulation translates a business decision, how many chairs of each type to make, into a clean mathematical problem that any LP solver can handle. Explanation: when an LP has only 2 decision variables, you can draw the feasible region on a graph and locate the optimum visually. Steps: plot each constraint as a straight line. For the example above, draw 2x plus 3y equals 200 and x plus 2y equals 150. Use intercepts. For 2x plus 3y equals 200 when x equals 0, y equals 66.7, when y equals 0, x equals 100. Do the same for the second line. Shade the feasible side, the side that satisfies the less than or equal inequality. The overlapping shaded area is the feasible region. Identify corner points, vertices of the polygon. They occur where 2 lines intersect or intersect an axis. Compute them algebraically. Intersection of the 2 lines. Solve 2x plus 3y equals 200 and x plus 2y equals 150. Subtract the second equation multiplied by 2 from the first. 2x plus 3y minus open parenthesis 2x plus 4y close parenthesis equals 200 minus 300 gives negative y equals negative 100, so y equals 100. Plug back to get x equals negative 50, which is infeasible. So the real intersection is at the axes, check each pair. Intersection with axes. 100 0 0 66.7 0 75 from second line 150 0. Evaluate the objective at each feasible corner. Open parenthesis 100 0 close parenthesis. Z equals 30 times 100 plus 50 times 0 equals 3000. Open parenthesis 0 75 close parenthesis. Z equals 30 times 0 plus 50 times 75 equals 3750. Open parenthesis 0 66.7 close parenthesis. Z approximately 3335. Open parenthesis 150 0 close parenthesis is not feasible because it violates the second constraint. Choose the highest Z for maximization. Here the optimal solution is open parenthesis x equals 0, y equals 75 close parenthesis with profit $3,750. The graphical method gives intuition. The optimal point always lies at a corner of the feasible polygon. Explanation: the simplex method solves any linear program more than 2 variables by moving from one corner basic feasible solution to a better neighboring corner until no improvement is possible. Okay, steps. 1. Standardize the model. Convert inequalities to equalities with slack variables. For the earlier example, add s sub 1 and s sub 2. 2x plus 3y plus s sub 1 equals 200. Next line, x plus 2y plus s sub 2 equals 150. And x, y, s sub 1, s sub 2 are greater than or equal to 0. 2. Create the initial tableau, a matrix that holds coefficients of variables, right-hand side values, and the objective row with negative profit coefficients. Example tableau. Basis column x, y, s sub 1, s sub 2 RHS. Row 1 s sub 1 2 3 1 0 200. Row 2 s sub 2 1 2 0 1 150. Row 3 z negative 30 negative 50 0 0 0. 3. Identify entering variable, the most negative coefficient in the objective row. Here negative 50 for y. 4. Identify leaving variable, compute theta equals RHS divided by pivot column coefficient for rows with positive pivot column entries. For column y, theta 1 equals 200 divided by 3 approximately 66.7, theta 2 equals 150 divided by 2 equals 75. Smallest theta is 66.7, so s sub 1 leaves. 5. Pivot, make the pivot element row 1 column y equals 3 equal to 1 by dividing the row. Then zero out the other entries in column y using row operations. 6. Repeat, after the pivot the new tableau shows a new basis, y and s sub 2. Continue until no negative coefficients remain in the objective row. When all are non-negative, the solution is optimal. The RHS values give the optimal values of the basic variables, non-basic variables are 0. Optimality criterion: no negative reduced cost in the objective row for maximization, which indicates optimal. The simplex algorithm is systematic, works for any size linear program, and always finishes in a finite number of steps. Though the worst case number can be large, in practice it is fast. Every primal LP has a dual problem that provides a second viewpoint on the same situation. The dual's variables represent the value of each resource, called shadow prices. Maximize C transpose X subject to a X less than or equal to B and X greater than or equal to 0. Minimize B transpose Y subject to a transpose Y greater than or equal to C and Y greater than or equal to 0. Economic interpretation: each dual variable y sub I tells you how much the objective would improve if the right-hand side of constraint I, the amount of a resource, increased by 1 unit. Example: return to the chair problem. Primal maximize profit. Maximize Z equals 30x plus 50y subject to 2x plus 3y less than or equal to 200 labor, and x plus 2y less than or equal to 150 wood, with x and y greater than or equal to 0. Dual variables: U equals price of 1 labor hour, V equals price of 1 unit of wood. Minimize 200U plus 150V subject to 2U plus V greater than or equal to 30 covering profit of standard chair, and 3U plus 2V greater than or equal to 50 covering profit of deluxe chair, with U and V greater than or equal to 0. Solving gives U equals 5 and V equals 10. Interpretation: each extra labor hour is worth $5 of profit, each extra wood unit $10. If the manager could obtain an additional labor hour at a cost less than $5, the overall profit would increase. Duality also guarantees that at optimality, the primal objective value equals the dual objective value, strong duality. Explanation: sensitivity analysis asks, what happens if the data change? After solving an LP, you can answer 2 common questions. Number 1, how much can a right-hand side constant resource amount change before the optimal basis changes? The allowable increase or decrease is found from the shadow price, dual value, and the range of feasibility. In the chair problem, the shadow price of labor, constraint 1, is $5. This means that if the labor hours increase from 200 to 210, an increase of 10, the optimal profit will rise by roughly 5 times 10 equals $50, as long as the increase stays within the allowable range, for example, 200 plus or minus 50 hours. Outside that range, a different set of corner points becomes optimal. Number 2, how does the objective coefficient affect the solution? This is a reduced cost analysis. Suppose the profit per deluxe chair rises from $50 to $55. The reduced cost for Y was 0 because Y was in the basis. The new coefficient would still keep Y basic as long as it does not violate the optimality condition. C sub Y less than or equal to cost implied by dual variables equals 3u plus 2v equals 3 times 5 plus 2 times 10 equals 35. Since 55 is greater than 35, the current basis would no longer be optimal. The model would need to be resolved, and likely more deluxe chairs would be produced. Sample calculation of shadow price. From the final simplex tableau, the row for a slack variable gives the dual value directly. If the row for labor slack S1 shows a coefficient of 5 in the bottom row, that 5 is the shadow price. Sensitivity analysis provides managers with a quick what-if tool without re-optimizing the whole model each time. LP models sometimes behave oddly. Recognizing these cases saves time. In feasibility, no set of decision variables satisfies all constraints. Example, x greater than or equal to 10 and x less than or equal to 5 cannot be true together. In a business context, it means the resource limits are contradictory. For example, demand for 100 units but production capacity only 80 and a contract that forces at least 120. The simplex will detect a phase 1 problem with artificial variables that cannot be driven to zero. Unboundedness, the objective can increase indefinitely while still respecting constraints. Example, maximize z equals x subject to x greater than or equal to 0 only. In a real setting, it means you have a product with positive profit but no limiting resource. For example, unlimited raw material, which is unrealistic. The model needs an additional constraint. Degeneracy, more than one basic variable takes value 0 at a corner, causing the simplex to possibly cycle. Example, constraints x plus y less than or equal to 10 and x plus 2y less than or equal to 20 intersect at 0, 0, where both slack variables are 0. Degeneracy does not affect optimality but may require anti-cycling rules, Bland's rule. Practically, it indicates a tight resource situation where several constraints are binding simultaneously. Understanding these special cases helps you diagnose model errors before spending time on calculations. Q1 formulation. A bakery makes 2 types of cake, chocolate C and vanilla V. Profit per chocolate cake is $12, per vanilla $9. Each chocolate cake needs 2 hours of oven time and 3 hours of labor. Each vanilla needs 1 hour of oven time and 2 hours of labor. The bakery has at most 40 oven hours and 60 labor hours per week. Formulate the linear program to maximize weekly profit. Answer sketch decision variables x sub c, x sub v. Maximize z equals 12x sub c plus 9x sub v. Constraints 2x sub c plus 1x sub v less than or equal to 40 oven, 3x sub c plus 2x sub v less than or equal to 60 labor, x sub c, x sub v greater than or equal to 0. Q2 simplex computation. Using the linear program from Q1, add slack variables s sub 1, s sub 2 and write the initial tableau. Perform one pivot to bring x sub v into the basis. Show the new tableau and state the basic feasible solution after the pivot. Answer sketch initial tableau. Basis xc, xv, s1, s2 right-hand side, s1 row 211040, s2 row 320160, 0, -12, -9000. Entering variable x sub v most -9. Ratio test, 40 divided by 1 equals 40, 60 divided by 2 equals 30, therefore s sub 2 lives. Pivot on row 2, column x sub v value 2. After row operations, the new tableau gives basic variables x sub v and s sub 1 with values x sub v equals 30, s sub 1 equals 10, z equals 270. Q3 interpretation. After solving the linear program, the shadow price for the oven constraint is $3 per hour and for labor is 0. If the bakery can rent an extra oven hour for $2, should it do so? Explain using dual economics. Answer, since the shadow price of oven time $3 exceeds the rental cost $2, each additional oven hour would increase profit by $3, netting $1